13th online lecture session of the course Engineering Thermodynamics. In our previous lecture, we have dealt with first law of thermodynamics. Then we have seen some different applications for estimating the amount of work done in different kind of systems. Apart from that, we have also seen the concept of specific heats, and we have defined that the amount of heat required to raise or change the temperature of 1 kg of a substance by 1 degree Celsius is referred to as specific heat. If this is done at constant pressure, then we call specific heat at constant pressure. If this is done at constant volume, then we call specific heat at constant volume. Okay, and then we have obtained the mathematical form for Cp and Cv, and later on we found that Cp and Cv are taking the form of all thermodynamic properties. So that's why Cp and Cv also we have referred as nothing but the thermodynamic properties of the system. Later on, I have tried to show the value of or the magnitude of formulation of specific heat, particularly for solids and liquids, and we have come up with the idea for solids and liquids Cp will be approximately equal to Cv, and we are defining a single specific heat. Okay. Now let us deal with the next topic, which is particularly related to specific heat of gases. Okay, so in terms of gases, so if I just give you the main formulation of Cp and Cv, we have seen that del H dH by del T at constant pressure is Cp, and Cv we have seen as nothing but equal to du by del T at constant volume. Okay, so now in terms of gases, what happens if we are having low pressure and high temperature? Under such assumptions, we will be having nothing but assumption of ideal gas as applicable. Okay, and moreover, particularly for gases, if we try to see, majority of the times we will be finding that we are having nothing but variation of properties as function of only temperature, not as function of pressure. Okay, so let me just show up this idea. So if you see my slide, in this particular slide, what I have done, I have presented the internal energy of superheated vapor. Okay, so superheated vapor is nothing but once again our gaseous phase. Okay, so what I am trying to show in this particular slide, that if we are having different values of pressure, so pressure I have taken in kilopascal. So for example, 10 kilopascal, 100 kilopascal, 500 and 1000, and temperature, corresponding temperature values are 200, 700 and 1200. Okay, so you can clearly see that this internal energy, while we are actually changing the pressure, so for pressure of 10 kilopascal it is 2661.3, for pressure of 100 kilopascal it is 2658, for pressure of 500 2642, and for pressure of 1000 it is 2621. So it means if we see at a particular temperature, for example, if we take a low value of temperature equivalent to 200 degrees Celsius, for that, when we are changing the pressure, the change in internal energy because of the pressure is actually small. Okay. Moreover, if we go to high temperature, for example, instead of 200, if I go to 1200 degrees Celsius, there I can see that the change of internal energy is even less. Okay, so this is obviously true, because when we will be going for very high temperature, then ideal gas assumption will be more valid. So under such condition, we can see that at high temperatures, effect of pressures is completely vanished. However, if we go for the low temperature, though there is certain effect of the pressure, but in comparison to the overall magnitude of the internal energy, the change of internal energy is actually very small. Okay, so it means that in case of superheated state or in case of gaseous state, for majority of our conditions, so where our pressure is not very high. So you can clearly see the pressure I am presenting over here in only kilopascals. Okay, so I'm not going to have extremely high pressures, because under these conditions the assumption of ideal gas will not be applicable. So if we take the moderate range of pressure and high value of temperature, even for the low value of temperature also, effect of pressure is actually very small. Okay, so from this particular table we can conclude that at high temperatures the effect of pressure is almost negligible. However, at low temperature there is certain effect of the pressure, but the whatever the change in magnitude of internal energy is happening, that change is actually very small in comparison to the absolute value of the internal energy. So because of that, this effect also we can neglect. Okay, so it means that if even I whether find the internal energy at 10, at 100 or 500, I can simply say that my internal energy is nothing but a function of only temperature. Okay, so this is one important conclusion we have made. We have made an important conclusion that for gases we have seen that our internal energy is nothing but sole function of temperature. Okay, so if internal energy is a sole function of temperature, in that case for gases I can simply write that my CV is equal to du by dt. Okay, I need not to write partial derivative, and I can simply write that it is nothing but it only depending upon the single parameter. U is only depending upon the single parameter temperature. So I can simply write that my CV is equal to du by dt at constant volume. Okay, so now let me go for the enthalpy. So if you talk about enthalpy, we have written that enthalpy is nothing but H equal to U plus PV. Now we are saying that if our gas is following the ideal behavior, I can replace this PV with nothing but RT. So if I write over here H equal to U plus RT, in that case what will be happening? My enthalpy is also becoming nothing but sole function of temperature. So if it is becoming a sole function of temperature, I can also write that Cp is also for a gas is nothing but equal to dH by dt at constant pressure. Okay, so now particularly for gases, under the assumption of ideal gases, these internal energy and enthalpy are becoming the sole function of temperature. So that's why we are actually avoiding the partial derivative over here, and we are writing derivative in the form of exact derivative. Okay, ordinary differential, and that we are writing as du by dt at constant volume for CV of gas, and Cp of gas we write as nothing but equal to dH by dt at constant pressure. Okay, now one important point here I would like to highlight, as we have already seen that almost all gases behaves as ideal when our pressure is approaching to zero. Okay, so when our pressure is very small, when pressure is approaching to zero, so under this condition each and every gas will be behaving as ideal gas. Okay, so by considering this assumption, what we do many times for ideal gases, we use the symbol Cp naught equal to dH by dt. So if we say that we are having any ideal gas, instead of writing Cp of gas, I can simply write Cp0. Okay, similarly I can write Cv0 as nothing but du by dt at constant volume. Okay, so if Cp0 and Cv0 is written, it clearly means that we are referring to the specific heat of the gases, because we are saying that these specific heats are taken when our pressure is actually tending to zero. If pressure is tending to zero, our gas will behave as ideal gas only. Okay, so because of that, many times these are also called as zero pressure specific heat at constant pressure. So, and similarly, if I talk about CV naught, it is also called as zero pressure specific heat at constant volume. Okay, so the idea of CP naught and CV naught is nothing but what we are saying, that directly we are saying CP naught equal to dH by dt, CV naught we are saying du by dt. Okay, so from here I can simply write for gases that my dH is nothing but equal to CP naught into dt and du is nothing but CV naught into dt. Okay, now we already know that our H equal to U plus PV, which is equal to H plus RT, sorry, U plus RT, because PV I can write RT. So now if I find out DH, DH will be nothing but du plus R into dt. Okay, DH I can replace with CP naught into dt, that will be equal to CV naught into dt plus R into dt. So dt will be cancelling, and finally we will be getting nothing but our CP naught. So finally, if I write over here, finally I will be getting that CP naught minus CV naught is nothing but equal to R. Okay, so this is one important relation which we will be finding after we take the assumptions of ideal gases. Okay, so after considering the assumption of ideal gas, we are finding that CP naught minus CV naught is nothing but equal to R, which is our characteristic gas constant. Okay, now let me show you some of the values of specific heat which are function of temperature. So you can see we have plotted CP naught by R along ordinate, and here temperature is given in Kelvin, and for different gases, for example, all the first you can see for all the noble gases we have actually variation of CP is actually independent of temperature. Then for all other gases, air, hydrogen, oxygen, this is how our actually CP values are changing. So you can clearly see that for majority of our gases, CP value is actually CP naught by R is actually increasing with increase of temperature. Okay, so that we can see. Now what will be happening while we will be solving the numerical problems for air. So let me just briefly tell you about this also. So while we will be solving the numerical problems for air, so air or any gas if we are having as working medium, while we'll be solving this type of problems, in that case what will be happening, we have to always take that CP naught is nothing but a function of temperature. Similarly, CV naught is function of temperature. Okay, however, what will be happening, for example, if my temperature is say varying from 100 degrees Celsius to 1000 degrees Celsius, we are having say certain table for CP and CV, and say we are having the value of specific heat given as x1, and somewhere here we have say xn. So we will be having multiple values x2, x3. Now if I am operating say in very moderate range of temperature, so for example, if I have variation of temperature from 100 to 300 only, and during that time there is not much change in between x1 to x3, so under such conditions what I can do, from this particular table I can simply define some CP naught average, which will be equal to, say if my range of temperature is from 100 to 300, so I can define some CP naught average is equal to CP naught corresponding to 100 plus CP naught corresponding to 300 divided by 2, and I can use this average value of specific heat. Similarly, I can do it for CV naught also, and I can use this average value of specific heat for solving my numerical problems. Okay, if we are having wide range of temperature in certain thermodynamic system, for example, temperature is changing from 100 degree to say 1000 degree. So obviously we will be having significant change in the magnitude of specific heat. So under such conditions, what we have to do, we cannot just take the arithmetic average. Okay, so if for certain gas behavior is completely linear, then obviously arithmetic mean will be serving the purpose. Otherwise, we have to find out the functional relationship of Cp0 as function of temperature, and then we have to substitute that function of temperature, and we have to do integration between our specified temperature limits. Okay, so what I'll be doing today, I'll be uploading one property table for air also. So in that property table only we will be having single dependent variable temperature. Okay, so with for different values of temperature, say T1, T2, T3, you will be provided with the value of Cp and value of Cv and R. Okay, so this particular property table will be applicable for air. So whatever the table I'll be uploading on the Moodle today, applicable for air only. Okay. Now let us go a little bit further into more concepts of our first law of thermodynamics related to closed system, and after that we will move our discussion for the open system. So before that, let me just briefly discuss about few more concepts. So one of the important concept that is something which is related to conservation of mass. Okay, so we see in terms of conservation. So what we see in terms of conservation of mass, normally, let me just explain with the help of example. So you can see that, so this particular concept now I am once again explaining with reference to the closed system only, and closed system are also known as fixed mass systems. Okay, so this I am explaining with reference to closed system or fixed mass system. So what we know from our understanding earlier, basic understanding, that if we are having a closed system, it means we will not be having any interaction of mass across the boundary. If we are not having any interaction of mass across the boundary, then obviously our mass of the system should remain constant. Okay, but ultimately if we have certain system where we are allowing the transfer of energy, so we are saying that energy of the system can actually change. If energy content of the system is changing, we know from our equation E equal to mc square that where we are having the change of energy, we will be having always change of mass. Okay, so because here in this particular equation you can see that energy is nothing but proportional to mass, but still while we are talking about our closed system or fixed mass system, we say that though we are having change of energy, we are having energy interaction, but still we are not saying that our mass is changing. Okay, so why? So let me just explain that part with the help of one illustration. So let us consider that we have some container, and inside this container we have a mixture of air plus fuel, and this mixture of air plus fuel is having certain initial temperature which can actually ignite this mixture. Okay, so now if I say that this my container is closed, so this is nothing but my closed system, because we will not be having any interaction of mass. Now let us consider that once this combustion has taken place, so initially in the fuel molecules, the energy was stored in the form of nothing but chemical energy. Okay, and then what will be happening? We will be having the process of combustion. While combustion will be happening, this chemical energy will be released nothing but in the form of thermal energy. Okay, and after the combustion, we will be finding that there will be certain release of heat. So we are considering that our air plus fuel mixture is in such a fashion so that say 2900 kilojoule of energy is actually releasing in this particular process. Okay, so finally what I'll be getting, that I'll be having my system which will be having now products of combustion. So now what I have, because this air and fuel mixture has oxidized, so now I'll be having actually products of combustion, and in these products of combustion now, while this fuel has oxidized with air, it has released 2900 kilojoule of energy, and I am saying that that particular amount of energy actually has released from products of combustion and it has gone to surroundings. Okay, so whatever the energy we were having, because of the combustion process, the temperature of the system has increased, and that increase of temperature, if we have to once again bring the system to thermodynamic equilibrium, that amount of energy will be actually released to our surrounding. Okay, so say whatever the amount of energy was released, that same amount of energy has transferred to the surrounding. So now you can say that at this particular second thermodynamic state, while system has reached, it has a loss of 2900 kilojoule of energy. Okay, so now if it is having loss of energy, obviously this system will be having certain loss of mass also. Okay, so now let us estimate how much mass loss we are having. So we know E is nothing but equal to mc square. So I can write over here 2900 equal to mass into c is nothing but speed of light in vacuum. So I can write as 3 into 10 to power 8 whole square. So if you use this calculation, and moreover here I have to actually, I am writing it in kilojoule, so that's why I have to divide over here with 1000. Okay, so now if you do this calculation, finally you will be finding that the mass whatever we are getting, that mass is nothing but equal to 3.23 into 10 to power minus 11 kg. Okay, so it means that while we will be dealing with our thermodynamic system, in case of our majority of the thermodynamic system, over here particularly now we are talking about closed system, while we are having the transfer of energy, whatever the mass change associated with that transfer of energy, that is very, very small. Okay, and the change of mass is so small that we can neglect, particularly from the macroscopic point of view, whatever we are trying to analyze in our subject of classical thermodynamics. Okay, so though in our thermodynamic system also we will be having some change of mass, while we are having change of energy, though there is no interaction across the boundary, there is no mass interaction across the boundary. However, the amount of energy and the corresponding amount of mass is so small that it is negligible in comparison to the overall energy content of the system. Okay, so that's why we can say that our mass is almost conserved in case of the thermodynamic system while we are studying these from the macroscopic point of view. Okay, now let me once again give you one more example. So that is related to the concept of work. So what I want to say we have a container, and in this container I have some partition over here. Okay, and in this particular left portion I will be having gas, and in the right portion I have nothing but absolute vacuum. Okay, so what I am saying, that I have a container and I have some partition. On the left hand side I have a gas, and on the right hand side I have absolute vacuum. Okay, now what is happening, we have the rupture of this intermediate wall. So if we are having rupture of the intermediate wall, so this gas will be actually occupying our entire system. So after the rupture, what will be happening? In our entire container, we will be having nothing but gas. So now you have to determine that while this transformation has taken place from state 1 to state 2, what is the amount of work which is actually done by the system. Okay, so that is something which we have to estimate. So if you have listened to the previous tutorial session, so which I uploaded yesterday, in that one I have already explained this concept, but let me once again quickly go through it for those who have not listened to the tutorial session. So what I am saying over here, that this is my gas, and this was the wall. So let me consider this as my initial system. So if I consider the portion of the gas only as my system, so what I am doing, gas portion only I am considering as my system. So in this particular case, what has happened, now this gas has actually occupied the entire volume of the container. So I can say that my system boundary has actually extended. So you can see, if I take only the gaseous medium as my system, so initially corresponding to first state, the gaseous medium was actually on the left of the intermediate partition, and while this wall has been ruptured, after that actually the gas has filled the entire container. So it means the boundary of system has changed from, because I am taking only gas as my medium, so the boundary of system has actually changed. Okay, so if now gas is boundary of the system has changed, so I can say that I have certain amount of dV. Okay, but because in this particular side we were having absolute vacuum. If we were having absolute vacuum, our pressure was nothing but equal to 0. So if pressure was 0, so it means if I say that while this boundary was expanding, what was the external pressure acting on the system? The external pressure acting on the system was nothing but equal to 0. So it means if I try to estimate the amount of work done, that will be nothing but equal to integral P external into dV, though we have some finite change of dV, but value of P external is equal to 0. So that's why our amount of work will be equal to 0. Okay, so this is like one of the approach for studying this type of system. Another approach could be that this is my first initial state. So let us consider gas over here. Another approach could be that I am taking this entire container as the part of the system. So if I take entire container as my system, so corresponding to that, this is my first state, and my second state will be nothing but entire container is my system. So system boundary is not changing. System boundary is as it is, and this whole system is filled with gas. So this is my state number 2. So now in this case, if you see, our system boundary has not changed. So dV is equal to 0. So whatever the changes are happening, these are within the system, and there is no interaction across the boundary, and boundary is not changing. So that's why dV is equal to 0. So under this circumstance also, if I do integral of P dV, that will be equal to 0. Okay. So such type of expansion process, if I just take the previous form, so in case of this particular system, what is happening? My system boundary is actually expanding against the 0 pressure. So such type of expansion where our system boundary is expanding against the 0 pressure, this type of expansion is actually known as free expansion, and work done in case of free expansion is equal to 0. Okay, so the meaning of free expansion is when our boundary of the system is expanding against the 0 pressure. Okay, now let me take up one more concept. So now what I will be doing, let us try to see the application of first law of thermodynamics. So we will take some system, and for that system we will now try to apply the first law of thermodynamics. So what I am doing, I have say some container A. I have say some container A, and then over here I have some valve, and another side I have another container B. Now let me say that Ma is the mass of the first container, Va is its volume, and Ua is the internal energy of this container. Mb is the mass of second container, Vb is its volume, and say Ub is the internal energy. And now what we are saying that initially whatever the valve we are having in between these two containers, initially this valve is in closed position. Okay, so once it is in closed position, let us consider corresponding to that we are calling our thermodynamic state as nothing but state 1. So that's why while I'll be specifying internal energy, I'll write over here U1A. I'll be writing U1A and U1B. Okay, so this is nothing but my, and similarly I can write V1A and V1B for the volume also. Okay, and now what we have done, so initially you may say that temperature also is actually different because internal energy content is different, so temperature can be different. So means this overall state of the system is say 1. So corresponding to 1, for first container I have 1A as the parameter, and corresponding to state 1 only for container B, the states are nothing but U1B. And U1A and U1B are completely different, they are not same. Okay, now what we have to do, if I just write the equivalent form after we have actually opened the valve. So now we have opened the valve. So once we have opened the valve, what we will be having? We will be having actually direct connection between container A and container B. Okay, so now my container A and container B will be actually directly interacting. So under this condition, what will be happening? I'll be having overall mass, say my thermodynamic state is 2. So M2 is say, now what has happened? Overall my system has actually, overall this is my system. So here also my system is including both the containers, but these were not having physical mixing. Now in this particular second type of combination, now we have the physical mixing, and corresponding to that say thermodynamic state is 2. So now both the mediums from container 1 and container 2 will be mixing, and finally let me say that M2 is my mass of the container. Okay, and say V2 is the final volume, and say U2 is overall internal energy now after this mixing process has happened. So this is nothing but a mixing process between the two mediums, and for this mixing process we have to determine the amount of energy associated with it, okay, or how its final properties are actually varying. So let me start the analysis. So first I'll be writing the conservation of mass. So based on the conservation of mass, what has happened, while initially we were having two different containers having mass Ma and Mb. So while we will be having mixing, our overall mass of the container, I can say that M2 will be nothing but equal to M1A plus M1B. So that will be my overall mass. Okay. Now if I write the first law of thermodynamics, so let me first specify the system boundary also, because whenever we will be analyzing the system, every time we have to specify system boundary. So let me consider that this is my system boundary. So over here also my system boundary is like this. Okay. So now if I write the first law of thermodynamics, as per first law of thermodynamics, we will be having Q122 minus W122 will be equal to, now I am considering this as nothing but my closed system. So because of the closed system, what will be happening? We will not be having any kinetic energy and potential energy. So we will be considering these as negligible. So this will be nothing but equal to our delta U. Okay. So if I just write it down, so Q122 minus W122 will be nothing but So delta U, if you see, that will be nothing but U2 minus U1. So what is your U2? U2 is very, very simple. Say if I say M2 is my total mass and small U2 is my specific internal energy. So I can simply write U2 as M2 into U2. And what is U1? So U1 was nothing but M1A into U1A was the initial internal energy content of the first container plus M1B and U1B was the initial energy content of the second system. So I can simply write M2U2 minus M1A into U1A plus M1B into U1B. Okay. So now if I divide throughout by M2, so I'll be finding 1 to 2Q by M2 minus W1 to 2 by M2 will be equal to U2 minus M1A by M2 into U1A plus M1B by M2 into U1B. Okay. So this term over here is nothing but M2. Okay. My overall equation if I include the work as well as the heat transfer. As our system boundary is not changing, so that's why work transfer in this particular case will be equal to 0, because our boundary of the system, whatever we have considered, that is actually not changing while we are having the mixing. Okay. And if we consider that our process is nothing but adiabatic. If our process is adiabatic, in that case, what will be happening? Q1 to 2 will also be equal to 0. So if Q1 to 2 is equal to 0, in that case, we will be finding that U2 will be equal to, so if I write the final equation after considering that internal energy is 0, I will be finally finding that U2 is nothing but M1A divided by M2 into U1A plus M1B divided by M2 into U1B. Okay, so it means this was nothing but the initial internal energy of first container. This was the initial internal energy of the second container. So it means this process is nothing but our adiabatic mixing. So if we are having adiabatic mixing where work done is equal to 0, our final thermodynamic state of the mixture will be nothing but equal to weighted mass average of the initial properties. So what we are having, nothing but weighted mass average. Why weighted mass average? Because you can see M2 is your total weight. So M1A by M2 is nothing but fraction of the mass of container A with reference to total mass, and this is the fraction of mass of container B. So if we apply that fraction to the energy amount it is possessing, we are getting some weighted mass average based properties, and these weighted mass average based property actually defining the final thermodynamic state of the mixing process. Okay. So similarly, like I have done this one for internal energy, similarly, we require one more parameter to specify the state. Okay, as per the state postulate, we require two thermodynamic parameters. So another thermodynamic parameter, I can take volume. So if I write volume conservation, volume will be nothing but equal to volume of first container plus volume of second container. So now we know that volume is nothing but mass into specific volume. So I can write this total volume as M2 into V2, that will be equal to M1A into V1 plus M1B into V1B. Okay, so finally I'll be finding that my final specific volume is nothing but equal to M1A divided by M2 into V1A plus M1B by M2 into V1B. So it means for this type of system, what we will be having? We will be having actually our properties after mixing as nothing but defined by weighted mass average of the initial thermodynamic properties. Okay. So this is about the mixing process while we are applying the first law of thermodynamics and our property equations, our basic rules of conservation to nothing but our thermodynamic system which we are trying to analyze. Now, till this particular point, whatever we have studied actually, that concludes our discussion on the first law of thermodynamics for closed systems. Okay, so now our next module will be first law of thermodynamics, and that we will be now studying for open systems. Okay, so that will be our next module. So what I will do now, I will stop at this point and I'll try to take up your queries, and we will start our next module from our next lecture.